So indeed, I would like to explain this construction, which will associate to a partial differential equation a group. So we'll go from PDEs to groups. And the case that we'll study is the Cordovec-de Vries equation. And we will consider, in order to obtain a group associated to this equation, we'll consider its so-called ultra-discrete limit, which is called box-ball system. We'll realize this using automata. Then via spectral theory, so at some point L2 Betty numbers will appear. Finally, we'll find a group which is in this case very interesting group from the geometric from the geometric point of view. Okay, so and this is a joint work with Tsuyoshi Kato and Satoshi Tsujimoto. And a part of this work already appeared, so it's in Communications, Mathematical Physics last year. Okay, so it's quite a long journey to arrive to the group. So let us start immediately. The Cordovec-de Vries equation we'll consider, it's really the most standard one. So namely, with one spatial variable, it's the derivative with respect to time plus the standard normalization x6 phi dx phi plus the third derivative with respect to x equal to 0. Okay, so as everybody remembers, it's supposed to describe the waves in shallow waters of Amsterdam canals. And everybody probably seen also discrete version of this equation when the spatial and the time variable, they take discrete values, say integer values, and the way to get the differential equation is by when you have the difference function at x and x plus 1, you replace, you scale the difference, so you replace 1 by epsilon, and by dividing suitable powers of epsilon, when one takes the limit, epsilon goes to 0, one obtains partial differential equation. Yet there is another way of obtaining a limit from this discrete versions. So one can consider so-called ultra-discrete limits. Ultra-discrete limits using using procedure which are related to so-called tropical geometry. And in this way, when one takes the limits, one also change the algebraic operations. So, for instance, multiplication can become maximum, And also the function, instead of taking integer values, in the limit, instead of in the limit, might take only only two values, say 0 and 1. So let me describe. I could write this again, this equation, but maybe let me, for this box ball systems, let me describe the evolution rules. I think it will be simpler. So we'll think about this function sequences of zeros and ones as the configuration of boxes. So there is a line of boxes which is infinite to the left and infinite to the right, and we have finitely many balls that we will put into these boxes. So say we'll have 4 balls. We'll put in the boxes as follows. Okay, so that's that corresponds to the sequence of zeros and ones, which is infinite to the left and to the right, and there are only finitely many ones. Okay, and what are the evolution rules? So there will be carrier going from left to the right, and the carrier will pick up the balls. Okay, so it picks up the first one, second, third, and as soon as there are empty boxes, we can start dropping the balls into empty boxes. Okay, so we drop 1 ball into the first one. We're still holding 2 balls. Right, so we drop the first one, we're still holding 2, we drop the second one, we're still holding 1, okay, but here is the ball, so we pick up this ball. Now we have 2 balls and we drop them to the first available empty boxes. Okay, maybe let us iterate this procedure one more time. Okay, so we pick the first ball, the second one. There is an empty box, so we will drop the ball into this empty box, and then we holding 1 ball. We pick up this one. Now we have 3 balls, and we drop them into the empty boxes. Okay, and now it's easy to imagine what will then happen. At each iteration, this 1 ball will move by 1 to the right, and this packet of 3 balls will move by 3 to the right. And also you can imagine what it looked before. We had this packet of 3 balls moving very fast to the right, and 1 ball moving slowly to the right, and at some point they let me call them waves. Okay, it looks like a soliton solution to the Cordovec-de Vries equation, when we have these 2 waves moving at different speed. At some point then interact, so something interesting happening, and after again we see these 2 waves moving at different speeds. Okay, so that's an indication actually when we look at these solutions to what is that this ultra-discrete limit is indeed corresponds to Cordovec-de Vries equation. And actually studying these box ball systems, it's a subject on its own. Apparently it's used in studying traffic jams in big cities. Okay, and also there is no reason to think that really like the language of physics is it's language of PDEs. Different phenomena in physics can be described well by this discrete systems. in order to see that there is a, to find the group which is associated to the system, we'll have to describe the evolution rules using automata. Okay, it will be very simple, but it's essential part of this construction. So I'll do it in the when we introduce one more parameter, which is very natural. Namely, we'll consider these box ball systems with the capacity. So let K be called capacity. So this is the maximal number of the balls carrier can hold at a given time. Okay, so once carrier picked up already K balls, when there is another ball, we cannot pick it up. Okay, we just pass. We go to the next box. Okay, so and actually I'll give you this automaton that describes the evolution rules in a particular case when the capacity is equal to 1. Okay, which means that at the given time we can hold at most one ball. Okay, we can hold one ball or no ball at all. Okay, if we have already one ball and see another one, we just go to the next box. Okay, we cannot do anything. Okay, so let me describe this automaton. The states of the automaton will be labeled by will correspond to the number of balls we're holding. Okay, so if the capacity is equal to 1, well, either we hold no ball at all or we hold one ball. So there will be just two states. Okay, and when we talk about automata, so of course we think about this configuration spaces as sequences of zeros and ones. Okay. Okay, so suppose we are at the state A0, so we hold no ball. If we see as entry 1, if we see a ball, we can pick it up. Okay, so if the input is 1, we pick up the ball, so the output is 0, and we go to the state A1. Okay, now we hold one ball. On the other hand, if we had no ball and the input was 0, it was empty box, well, nothing happens. Okay, so input is 0, output is 0, and we go back to the state A0. If we are at the state A1, so we hold one ball. If we see empty box, okay, so if the input is 0, we drop this ball. So the output is 1, and we dropped the only ball we had. So we go to the state A0. On the other hand, if we are in the state A1, we hold one ball, and the input is 1. So we see a ball because we already reached the maximal capacity. We cannot do it. We do nothing. So the input was 1, the output is 1, and we are back at the state A1. And everybody can imagine the description of an automaton corresponding to arbitrary capacity. So it seems like a very easy observation. However, it's essential to see the relation to the group theory, and we really exploit this remark, the fact that the evolution can be described by an automaton. And indeed, the link will be via spectral theory. Okay, so let me describe this this link. So actually, this talk I would like to somehow present on two levels. So on the one level, I'll describe just this procedure, how you can find this group, and it will be really elementary. Okay, so there is no excuse not to understand. Okay. But parallel to this, I will try somehow to relate this procedure to notions like Phenomen Dimension and L2 Betty numbers in order to show you that actually it's where this procedure comes from. But from the formal point of view, it will be very elementary. Okay, so let us describe the operator that we'll be interested in. So we'll restrict our attention to finite sequences of zeros and ones. Okay, so we'll take a finite sequence of zeros and ones of length n, and if we start our automaton at one of its states, for instance a0, okay, and we follow the rules given by this automaton, it will define as a map from sequences of zeros and ones of length n into sequences of zeros and ones of length n. Okay, so A0 n is this mapping, which actually could be described by matrix. Okay, so the dimension is the number of the sequences of zeros and ones of length n. So it's can be described, this mapping, by the matrix of the dimension size 2 to the n times 2 to the n, where we put 1 if the well, so we label this all the sequences by numbers from 1 to 2 to the n, and we put 1 on the ith j coordinate in the if the ith sequence is mapped into jth sequence. Okay, so it's this matrix with coefficients 0 and 1. Okay, and similarly, well, we can start at the state A1. So in this way, we obtain another mapping. Okay, and the operator we'll be interested in is the sum of these two plus the adjoint transposes of these matrices. Okay, and actually let me call it M as Markov operator, because if we normalize, if we divide it by 4, the matrix that you find here is a bistochastic. Okay, the sum of the sum columns and sum of the rows is equal to 1. Okay, so okay. By the way, it's an interesting situation. So here, in some sense, we are already in the case or group case. So the fact that this after normalization it would be a bistochastic matrix, it's a general fact if these mappings are bijections. Okay, and of course, well, if you have bijections, you can define a group. However, it's not the case. It's not the case here. These mappings are not invertible. Okay, and indeed, kind of so the story could be much shorter. if these mappings were invertible, because there is a general theory of groups generated by automata. So if you deal with an invertible automaton, you can associate to this group. Actually, if you would like to know more details, at some point I wrote Bourbaki seminar about this. Called automata groups. Okay, so it's a very interesting construction. So here, in order to find a group, at some point we have to use probability. We have to use this Markov operator, and we'll see how it enables us to find a group. Okay, so we'll be interested in eigenvalues of this matrix, and we'll compute them explicitly, and but in particular we'll be interested in the asymptotic behavior of eigenvalues and their multiplicities when n tends to infinity. So in order to compute it, it's really essential that it's fundamental that these matrices are related to an automaton. Okay, so namely, they are kind of self-similar. So on the level of matrices, you have the following recurrence. If you look at the matrix A0 n plus 1, okay, you can then compose it into blocks. Okay, so here we look at the sequences of zeros and ones which start of length n plus 1, which start with 0, and here the ones which start with 1. Okay, so then if you look at this automaton, okay, if you have 0, the output is 0, and we go to and we are back to the state A naught. Okay, so actually here you find the matrix A0n. Okay, on the other hand, if the input was 1, the output is 0, and we are at the state A1, so here you would find the matrix A1n. Okay, and here below the matrix is 0 and 0. Okay, so by the way, so here it's clear that it's not an invertible, mapping. Okay, however, and you can find a similar recurrence rule for A1 n plus 1. Okay, however, if you consider this sum, you are in the invertible situation. Okay, very well. So it enables one to find explicitly eigenvalues and their multiplicities, and we'll be interested in the asymptotic behavior when n becomes large. So we'll define limit multiplicity of the eigenvalue lambda. So it will be multiplicity of lambda in the spectrum of this operator, maybe. Multiplicity of lambda in spectrum of Mn, okay, and we'll divide this by, we'll compare it with the size of this matrix Mn. So the size is 2 to the power n, and we'll take the limit when n tends to infinity. Okay, so we fix lambda, and we look how its multiplicity in the spectrum changes with n, and we'll take the limit when n tends to infinity. Okay, in general, there is no reason why this limit should exist, but in case it exists, one can compute it. So let us see. Let me state the result. Okay, so the limit multiplicity of lambda, which is equal to 4 cosine pi p over q, is so here, well, let us suppose that p and q are relatively prime. So the limit multiplicity is 1 over 2 to the power q minus 1. Okay, so the only numbers which appear as eigenvalues of these operators are of this form, and they appear with large multiplicity. So for it's roughly 2 to the power n times this coefficient. Actually, it's a right moment to mention Euler here. So if you take the sum of all these limit multiplicities, so we take each number as many times as there are numbers relatively prime to q. So it's phi, the Euler function phi of q. The sum is from q equal to 2 to infinity, 2 to the power q minus 1, it's equal to 1. Okay, so this is due to Euler, which indicates that there are no other eigenvalues, right? That if you sum all these multiplicities, because here we divide by the size, so the sum of this normalized multiplicities is equal to 1, and in the limit again we find 1. Okay, this is actually another way of proving this result of Euler. Okay, so here maybe I'll stop the story. Only at the end we'll see the group. Let me try to explain you this procedure, also this limit multiplicity in case of groups. So okay, so let me now talk about L2 numbers of closed manifolds. Which were defined by Atiyah in 70s. So there are homotopy invariants of closed manifold. Okay, it can be defined by for any closed manifold. The definition we will see is in the case when the fundamental group of this manifold is residually finite. Okay, so it means that there is a sequence of finite index subgroups which we're supposed to be normal. Their intersection is trivial, and also for this the definition we'll suppose that it's a descending sequence. Okay, so examples of residually finite groups, well, you can take integers, and then this approximating sequence of this finite quotient gamma modulo n, you can take z modulo n. Here I added this technical condition, so maybe we should divide by 2 to the power n, or more generally, if you take any finitely generated linear group, like group of matrices like SL3 Z, then as this sequence of finite approximations, you can take the coefficients modulo n. Okay, so in this situation one can define the ith L2 Betty number of this closed manifold as the limit when one takes the finite covers of M. Okay, so it's universal cover of M modulo gamma n. One computes the usual ith Betty number, and one divides by the degree of the covering. Okay, so this is the index of gamma n in n, and one takes the limit when n tends to infinity. So actually, we will see that what we are doing here corresponds exactly to this definition of L2 Betty numbers. For this, the only thing we'll have to see is to realize that the operator like M, like this Markov operator, can actually correspond to the Hodge-Laplace operator, which computes Betty numbers. Okay, as you remember, the usual Betty numbers can be computed as dimension of the kernel of this operator. Okay, and we'll see that L2 Betty numbers as well, and indeed they correspond to this limit multiplicity. Okay, so let me explain how indeed L2 Betty numbers can be computed. Let me give you an analytic definition of L2 Betty numbers. This definition certainly does not explain why they are called L2. Where is the analytic analytic condition. So in order to do this, I'll remind you the definition of Phenomen dimension. So it's we will define dimension kind of more density for subspaces in the Hilbert space of infinite dimension. It will be continuous, so-called continuous dimension, the number between 0 and 1. And von Neumann had this idea that, well, so you know that, well, if you take all Hilbert spaces with countable bases they are isomorphic, but in order to define this von Neumann dimension, we'll have to realize the Hilbert space as L2 of some group. Okay, so this is this is great news for all who are interested in group theory, that you really need groups to do it. So it's von Neumann dimension, which can be defined for the subspace of L2 of a countable group gamma. Okay, and in order to have good properties of dimension, we'll also suppose that B is closed and gamma invariant. Okay, we'll see that these are conditions which are satisfied in our case. And then one can define this von Neumann dimension of the subspace B. So what we do, we take the projection on the subspace B, we apply it to the function delta identity. So this is the function which is equal to 1 at identity of gamma and 0 elsewhere. Okay, we project it on the subspace B and evaluate it at identity. Okay, so we take the scalar product with delta at identity. Okay, so this is a number between 0 and 1. Okay, it's like density of this subspace. It's called dimension because if you consider the direct sum, it will be the sum of dimensions. It's also 0 only for the trivial subspace. Okay, excellent. So that's the definition of the von Neumann dimension. And L2-Betty numbers are computed as the von Neumann dimensions of the kernels of the operators of the following form. So if we consider an element in the group ring, okay, so formally it's a finite sum of elements in gamma with integer coefficients. Okay, and so A, this is a finite sum of AI, gamma I, AI are integers and gamma i's are elements in the group. Okay, it defines a bounded operator from L2 of gamma into L2 of gamma. Okay, it acts, so if one takes a function L2 of gamma, A acts on this function, we take the translations by elements gamma I and sum of these translations multiplied by this integer coefficients. Okay, and this L2-Betty numbers are computed as the von Neumann dimensions of the kernels of this operator. Okay, so it follows from the combinatorial definition of L2 numbers due to Dojuk, that so actually, let me state it. Okay, so the fact. Let gamma be a group which is a fundamental group of closed manifold. So let gamma be a finitely presented group. Okay, and let A be any element in the group ring. Okay, then there exists a closed manifold M such that the group gamma is the fundamental group of this manifold, and one of its L2 numbers, actually let me to be explicit, so say the third L2 number of this manifold, okay, is equal to the Phenomen dimension of the kernel of A acting on L2. Okay, so of course, well, the kernel of A is closed, and if A is given by such operator, it's also gamma invariant. The kernel is also gamma invariant. Okay, so what if you now look at this definition? So what you have on the left hand side is the Phenomen dimension of the kernel of, say, like something like Markov operator, what we've seen, okay, and what you see on the right hand, okay, is the dimension of the kernel of this M acting on this finite covers. Okay, so it exactly corresponds. So here we're talking multiplicity of 0, the kernel, and here we have the dimension of the kernel for this finite approximation. Okay, so indeed, if we are in the group case, what we are doing here, we are computing Phenomen dimension of some operator acting on an infinite group. Okay, so we've seen. So actually, it can be also another interpretation is the computation of the Phenomen dimension using finite quotients of the group. Okay, maybe let me give you yet another way of computing Phenomen dimension, also using finite approximations. Okay, so here we've seen this computation for groups which can be approximated by finite groups, for residually finite groups. And let me give you another way of computing it for so-called amenable groups. This is another notion due to von Neumann, and both ways are interesting for the group in question, because it's both residually finite and also amenable group. Okay, so let gamma be an amenable group. Okay, which means that we have a sequence of finite subsets in gamma, okay, A, N are finite, and there are more and more invariant under translations. So namely, if you consider AN and the symmetric difference with AN translated by gamma, okay, and you compare it with the size of AN, when n tends to infinity, this limit is equal to 0. Okay, and this is the case for any element in gamma. Okay, so an example of such a group is, for instance, you can take integers, and then this subsets AN, you can consider the numbers from 1 to n. Okay, and these long intervals, there are more and more invariant under translations. And in order to compute the Phenomen dimension, we can use this approximating sequence AN called Fellner sequence. So namely, for any element, let me use the same letter as before. Hope it won't confuse you with the Fellner sequence. So for A, an element in the group algebra, one can compute its Phenomen dimension, the dimension of its kernel, okay, acting on L2, as follows. So we will consider A acting on function on this finite subset. Okay, let me write it just L2 to say that we're considering the functions, although it's a finite set. So we consider here O functions. So A will act here as follows. If we take a function on the subset AN, we extend it by 0 to the whole group. We apply A, and then we restrict again to AN. Okay, and well, so if here we consider the dimension of the kernel, the usual dimension, and we'll divide it by the size of AN, and when we take the limit, when n tends to infinity, we'll find the Phenomen dimension of the kernel of AN. Okay, so for the groups like integer, you can use either as the sequence will quotients, you can take z modulo n, or you can consider these intervals from 0 to n. Okay, very well. Actually, to get, in order to gain some intuition concerning that there are many interesting connections between spectral properties of this operator, Phenomen dimension, and algebraic properties of the group. It's actually really very deep and interesting connection, which can be expressed on several levels, purely algebraic, it can be expressed in the context, in this L2 context, in the phenomenal, in the context of Phenomen algebras, and also in the case of C-star algebras. In a sense, I think, yeah, there is too much that could be said about this. It's okay. So right. So now, we understood this procedure in the case of groups. What is the interpretation of this limit multiplicity? So now let me explain what is the group that one can find. One finds using this procedure. So it will be the Lamplighter group. Okay, Lamplighter. The Lamplighter group. So its algebraic structure is the following one. Can be this. It's a direct limit, direct sum of Z mod 2 over Z, semi-direct product with Z. Okay, so Z will act on the basis by translations, and so what are the natural generators for the group? So there is a generator for Z, let me call it T, okay, and a generator of one copy of Z mod 2, say at 0 position, that we'll call it A, okay. So A is of order 2, T is of infinite order. And now, if you consider the following element in the group, so this operator, the following element in the group algebra, so we won't take what will be natural to take A plus T and the inverses. What we'll do, we'll take T plus AT plus T inverse plus AT inverse. Okay, so this is the element in the group algebra that we consider, and if you consider now this finite quotient of this group, if you take it Z modulo n, you will find and you will look at the action of this element in the group algebra of this finite quotient. You will find the matrices, and you will represent it as the as we explained before by matrices with zeros and ones. You will find the matrices which are conjugated to the matrices that we defined for this ultra-discrete limits of Kordovec-de Vries equation, box ball systems. Okay, so indeed the computation we did corresponds to the computation of the Phenomen dimension of the kernels of the eigen spaces of this operator A acting on L2 of this group. Okay, and indeed this Euler formula, it corresponds to the sum of the Phenomen dimensions of the eigen spaces of this operator. Okay, thank you very much.
Remarks? No questions.
So no, I have a question. So I didn't understand what the correspondence between Korteweg de Vries, so some properties of Korteweg de Vries and some properties of box-ball systems. So how do they correspond?
Right.
So how the properties correspond? So if you have some answer for box-ball systems, what can it tell you about the initial Korteweg de Vries equation?
All right. So okay. So we having here PDE. We having here a discrete version of it, and also this ultra discrete limit. Okay. So this studying ultra discrete limits. This is very recent. As far as because your question is very general, so already you can ask about. Right. So already one can talk about connection between this PDE and discrete version. Okay. So it's like a step in between. So actually here I would this was very much studied, this like discrete Laplace operator. So I would say that it's very difficult actually to obtain get formal translation of some result concerning continuous case and discrete case and vice versa. So the way I see like the history of subject is that different properties were established like separately. Okay, you would prove some property for the continuous Laplace operator, and in order to obtain the similar property in the discrete case, you really have to do it separately. So, for instance, there are results with recently found really spectacular applications concerning well the kernel of such operators on functions when you put some condition on the growth. Okay, say like so. Functions which are in the kernel are called harmonic functions. So we can look at the harmonic functions of say polynomial growth, and in case of results which were known for the continuous case, the similar ones, namely that this for some groups that the spaces are of finite dimensions, the results are the same. However, the proofs are separate. Okay, it's not that you can formally take the results and say that because it holds in the continuous case, it should hold for the discrete. So now you can. I could give you several cases of really amazing applications of this kind of results. However, my impression is that so it's never really direct consequence, but you have to prove such results separately. Okay. Now for this ultra discrete limit, so it's much more recent. It's like beginning of the history. But again, I think it won't be like this, that you will be able to translate results from Korteweg de Vries, these things I mentioned at the beginning about soliton solutions. Okay, it's kind of you work separately in KDV. This is just, but you find the same phenomena. So I think the way I would see the theory is more by like taking results from one side and trying to find the analog on the other side, but I doubt you could do it directly. In the case the passage discrete continuous case, it's somehow sometimes very difficult actually to establish analogous results, and there are many many conjectures which are open for a long time before they were established in the discrete case, when they were well known for a long time in the continuous case. Okay, so I doubt you could do it, and this discrete case, it's really like in between this ultra discrete limit and continuous. And also it's formal. I could well, I don't have time here, but it's not so difficult to describe this procedure, this ultra discrete limits, how you obtain them from the from the continuous case. However, the interpretations for these box-Bose systems, they are really it's really different. The box-Bose systems, they find the like somehow they are interesting for their own sake. Okay, they correspond to other different phenomena. But it's, I think it's very enriching to like think about these two being related, and here you have yet another connection to group theory. And as far as this Lamplighter group is concerned, there are many results concerning this group. It's like classical example in the theory of random walks on groups for a long time. So it arrives with a lot of like results on which were established for this group. Okay, and it's also interesting that we were talking really about the. So of course, for Cordovec-de Vries, you have many variants for BBS, you have many variants, and also for the Lamplighter. Okay, there are, but what we see, this connection we've seen, are really for the simplest cases. Okay.
Any other questions? Yes.
If you start with a different, somehow related equation and do the similar procedure, what kind of geometries can you obtain? So here you get to the Lamplighter certain solvable case. For example, do you, I don't know, can you obtain the mean field hyperbolic?
So this is the beginning of this story. It's it was done only for this for the Cordovec-de Vries equation, and there are many like the way of getting from this from the PDE to a group. There are several steps, and it's not clear why it should work in general. So one of the places that should be stressed here is this passage I described, how from an automaton obtain a group. Okay, so what we were getting was a semi-group. Okay, and it would be, for instance, interesting to understand in which case this kind of introducing probability, considering this Markov, well, I want to say Markov operator. Indeed, I said that in our case we obtain by this procedure this bistochastic matrix, but it's not clear if this would work in general. So it remains to, like, I think it's a procedure that could be, one could try to apply to other equations. However, there are several steps where it's not clear if it's going to work.
I also have a final question. Right?
Yes.
You have a lot of information about the Lamplighter Group, the spectrum, the spectral zeta function, the behavior of the random walk, different asymptotics. Do any of those appear in some way related to KdV equation without knowing the connection? Do you see any of those behaviors associated with the Lamplighter in the KdV?
So it seems to me that it's really new connection. The way the group arises here. So of course, well, normally you see the groups arising as groups of symmetries, and this is a new way of it is a really new way. The group is associated to partial differential equations. Okay, it doesn't arise as the group of symmetries and so on. And here again, so I would like to say that because this question kind of it's like it's a continuation of the question that was asked at the beginning. This like relations of between this continuous case and the discrete case. So well, as far on the level of this box-ball systems, there are some relation. It was known kind of a relation for the to some zeta functions, but again, it's like I don't think you can really. I don't think you can really translate results when you get this limits. Again, I really see it. I don't think one will be able really to translate results from this continuous to discrete case. The only way I could see is by by really proving similar results, okay, from the corresponding.
It was not my question, but it doesn't matter.
Sorry?
It was not my question, but it doesn't matter.
So what was your question?
Whether some of the things that you know for Lamplighter, you observe them without having a translation or a direct connection, whether some asymptotics that are known for the Lamplighter appear in some way for the KdV. Probably you also know a lot of things about the behavior of solutions, some asymptotics, whether some similar asymptotics appear in that continuous situation without necessarily having a direct connection or translating them. Basically, whether you had any indications that in the limit what you are going to get will be this particular group, whether you could guess it without having any explanation by seeing some similarities. So I during the talk I indicated, for instance, this in between BBS and the Cordovec, there is these solutions which look like solitons. Okay, so this is.
Other questions? Then let's thank the speaker again.